The title of my talk is Design of Comp-Based Decimators for Sigma-Delta Analog Digital Converters. My name is Gordana Dolecek, and I am coming from Institute in Puebla, Mexico. The outline of my talk is the following. First, introduction. After that, I will say something about SiC filters, and I continue with improving aliasing rejection and improving passband characteristic, and finally improving simultaneously stop band and passband. Finally, conclusions are given. Let's start with the introduction. Oversampled sigma-delta converters have become widely used as a valid alternative to conventional AD converters operating at the Nyquist frequency. There are many advantages like high resolution of reconstructed data and an easy implementation in a single VLSI chip, among others. Unlike conventional AD converters, an oversampling sigma-delta AD converter samples the analog input signal with a frequency much larger than the Nyquist frequency. Sigma-delta architecture, robustness, and properties are a result of this oversampling. Later, the rate of the oversampled signal must be decreased to a Nyquist frequency. This process is performed in the digital form and is called downsampling. As a result, sigma-delta AD converter consists of two parts, sigma-delta modulator and decimator stage, which decreases the oversampled frequency of the modulator to the Nyquist frequency. However, the downsampling introduces the aliasing, which maybe deteriorate the signal and as a result must be eliminated. This is why we need a digital filter before the downsampling. This filter is called decimation or anti-aliasing filter. Digital filter and downsampler are called decimation stage. As shown here, we have one decimation stage, here's a filter, and here is block which change sampling rate by one integer factor denoted as n and is called downsampling factor. The key part of decimation stage is a decimation filter, which is responsible for aliasing rejection. However, this filter cannot be a bottleneck of the total design, and it is very important to design a simple decimation filter with high performances, high aliasing rejection, and high signal preservation. The simplest decimation filter is so-called SiC filter. SiC is an abbreviation of Cascade Integrated Comp filter, and the structure is shown here. We have three blocks. First block is block integrators, and this is block of comps. And here is inside is downsampling by M. The system function of SiC filter is given in this equation. SiC filter is usually used at the first decimation stage, while a second decimation block with the decimation factor R is smaller than that of SiC filter. The factor R determines the frequency at which the worst-case aliasing occurs and the passband edge frequency where the worst-case passband distortion occurs. For example, in the case of factor of R second decimation, the passband edge of interest normalized for the high sampling rate is given in this equation. Similarly, the worst-case aliasing is at frequency expressed in this second equation. Consequently, the SiC filter must have a low passband droop in the passband determined by omega C, and enough attenuation in so-called folding bands, EA bands defined around the zeros of SiC filter As shown in this equation, this is frequency characteristic of SiC filter. Here are zeros of SiC filter, and bands around zeros are called folding bands. And these bands must be high attenuation. All other bands don't have bands. Here is a pass band, and the characteristic of the filter in a pass band must be flat to avoid deterioration of decimated signal. Some things could be improved in application of SiC filters in decimators. The integrator stage works at a high input rate, high power consumption. This can be resolved by using non-recursive structure. Other problem is that frequency response, which is given in this equation, doesn't satisfy design specification. That means that there are not enough aliasing rejection, or there be high passband drop. Various methods have been advanced to solve these SiC filter problems. Methods can be divided in three groups: methods for stop band improvement, methods for passband compensation, and method for simultaneous stop band and passband improvement. In continuation, I will talk about all three methods. Let's start with improving aliasing rejection. The popularity of SiC decimation filter is due to its simplicity. SiC filter is a multiplier-less filter. As a result, the filter used to improve SiC filter characteristics is desirable to be also multiplier-less filter. Different methods to improve SiC aliasing rejection were proposed, like using cosine filters, sharpening with a Chebyshev polynomial, using a cone variant, combs of different lengths, etc. The most recent methods explore certain characteristics of symmetrical polynomials to introduce additional zeros in cone folding bands, to widen the folding bands and thus increase aliasing rejection. Exploring the characteristic of symmetric polynomials was proposed the modified cone cascading the original cone filter with filter H12 presented in this equation. As a result, two additional zeros around the cone zeros in folding bands are obtained and shown in the next figure, where the parameters are set as m is 5 and k is 1. This work is presented in this reference presented here in 2017. Here we have zeros of comb filter, and cascading with the filter H2, we get around each original zero, we get two additional zeros, as shown in this figure. And as a result, magnitude characteristic shown in green has a wide band, wide folding bands, and as a consequence, higher attenuation in folding bands. And now I will say something about improving passband characteristic. The compensated magnitude characteristic should approximate an inverse cone magnitude characteristic in the passbands, as shown in this equation. C is a magnitude characteristic compensator, and H is a magnitude characteristic of the cone. Must be this inverse relation in the passband. Compensator usually works at a low rate, that means after the decimation by m. As shown here, here is decimation filter downsampling, and here is compensated. Using multi-rate identity, we can write system function of compensated filter as h of z c z on m. Different methods have been proposed to design compensators. Generally, The compensators are designed as FIR filters to have a linear pace. A multiply-less method like interval analysis method, amplitude transformation, using sinusoidal function magnitude response, particle swarm optimization are methods used for design of compensator. In this presentation, I will present one design presented in this reference in 2021, where compensator has magnitude response synthesized as a sum of sine waves, where the amplitudes of sine wave functions are obtained by particle swarm optimization method. We have here magnitude response of compensator, and A and B are two parameters. And corresponding system function is presented in this way. We have two coefficients C0 and C1, which are related with the parameters A and B. And this compensator has two coefficients and 6 others. We can have multiplier-less design, where design with multiples, where C0 and C1 are multipliers, or present this value in SPT form and have multiplier-less design. We propose two design with multipliers and without multipliers. In the first design, the compensator is a 4-order FIE filter with two multipliers and 6 others. In the second design, the coefficients are presented in the signed power 2 form, resulting in a slight increase of the passband deviation compared to the first optimal design. The number of others is varied to get flexibility of design. This is illustrated in an example where we have M is 16 and K is 3. Compensator parameters A and B obtained using particle swarm optimization and have the values of which are shown in this display. The absolute value of the maximum passband deviation in compensator curve is 0.0185 decibels. And the result is presented here. Non-compensated comb is with the green line and compensated comb with the blue line. In multiplier-less design, the optimal coefficients are presented in SPT form. We have four design which needs a different number of others. All four designs are illustrated in this figure with a different color. Blue for first design, green second, red is third, and fourth design is this presented here, and it requires 9 others, and this first design requires 6 others. We can see that there is a trade-off between quality of compensation and required number of others. Now I will say something about improving simultaneously stopband and passband. I present classical sharpening comb method presented by Quintus and Wilson. They improved comb magnitude characteristic in the passband and also in folding bands by using sharpening polynomial, which were to sharpen a comb filter characteristic H, which is presented here. Sharpening system function of sharpened comb filter is given in this equation. As a result, we have improved passband characteristic as shown in this zoom below, and also improved attenuations in folding bands. Finally, I give conclusions. SIC filter is the most simple decimation filter. However, its managed characteristic in the pass band and stop band is inconvenient in many applications and should be improved. We presented some methods for pass band improvement, stop band improvements, and simultaneous improvement of pass band and stop band. Thank you very much. And here is my email for any questions. Thank you.